Hey guys, how's it going? I am back and I'm going to be going over another CS interview question about system design. And in this video, I'm going to be going over designing a web crawler. And I'm going to be going through the interview process, like how I would approach it. So this is not something that I've prepared beforehand. You're going to see the live thought process as I go through it. So designing a web crawler. So if you're not familiar, a web crawler goes between each website and then crawls between traverses the internet to find different websites and captures the information on these URLs and then stores it in some sort of database. If the web crawler was, for example, for use case for Google, it would go through with the goal of acquiring links and storing in some sort of database to reference later. So let's define the use case of the web crawler. And in this case, we are going to be using Google. So what does our web crawler do? It goes through a root sort of website, and from the root, it traverses all the A tags to find secondary websites. And then from these secondary websites, it does the same thing and then looks for the links and then finds another website, and then so on and so forth. You can sort of get the inference that it's going to keep on doing this until it hits the end of the internet, which is really impossible. So how do we design this? For the use case of Google, what this web crawler is going to do is it's going to take the body of the website. So if this represents a website, it will take the body of the website. So let's say this is a body tab. And it's going to take all the text in between here and it's going to store it in some sort of database. And this database can be SQL, NoSQL, it could be just a key value store like an S3 bucket, or it could be a big table. We don't really know what it is. We can just call it a black box and call it a database for now. So this is basically what the web crawler will do. Of course, there can be some ML scripts and stuff like that. So let's design the system. So now we know like the basic functionality of what this web crawler is going to do. Let's start getting the system down. So what we're basically doing is a graph first, a breadth first search, a monograph, which the graph represents the internet. So we would need, to build this kind of system, we would need I'm gonna make this round because I think round rectangles always make for a good system design. And we can have the crawler. So what this crawler will do it will traverse the internet, and when it finds a node, it's going to be putting it onto a queue. So what this queue represents is the frontier. The frontier is the list of all the links that still need to be traversed. And when it gets a list here, it's going to give the link to the crawler, to traverse next. And is going to be repeatedly doing this throughout the entire length of the um, of the um, of the crawling. So in order to do that, our crawler needs to have a couple features. So a couple of those features are, it needs to have some sort of HTTP processor. This HTTP processor needs to be able to find links. And then it needs to be able to also insert information onto a database. So if it can find information and put it onto a database, then it also needs to store onto a database. If it finds a link, then it needs to check if it has been visited. So we would also need a node to check if visited or not. I'm going to pause real quick. So it needs to check if it has been visited, and if it has not been visited, then we need to place it onto the queue. So now we have the basic system down of what happens when we crawl the internet. Then this really starts so now this really begs the question of some analysis. Based on our information, we are going to have very different databases and are going to need to break down this information onto DB step and store into DB step. So it would be fair to assume that if we strip all the information down from a HTML page and only get the relevant information, which includes the paragraph, the H1, the H2, H3, H4, H5, that we could likely compress it to below 4096 bytes. So let's run this as an average per web page. That comes out to 4,000 characters per web page. A typical blog article will probably have around 1,500 words. So likely 48 bytes would be more accurate for this. So per web page, up to 2 kilobytes. So if we have 2 kilobytes per web page, and we were traversing the internet, a typical website would likely have around, say, 20 blog posts or relevant web pages. And there are over a couple million websites. All of the websites up to 4 characters are taken, which comes out to 26 letters in the alphabet to the 4th power. Let's say like everything up to 5 characters is taken. So we know up to 5 characters is guaranteed to be taken. So that comes out to around 1,200,000 websites. And likely it's going to be more, so we can add a margin of error and just round to the 6th power. So 308 million websites. So 20 relevant web pages per website with 2 kilobytes per web page. This comes out to 106.568 million bytes, which is, means this is megabytes, gigabytes, terabytes, and this is for one full traversal of the internet. So 12.6 terabytes of storage, which honestly is probably of a low number. This is probably a very conservative estimate. It's probably going to be in the petabytes, honestly. But this would be like a good lower bound. I guess for just safety's sake, we should really round this to 40.96 terabytes of storage for one full traversal. So now we should store it into the database, and each item, one entry is 20. We would have to keep the URL. We would have to keep the data. And then the data traversal. So if we were to convert that into something more computer readable, that would come to, let's say 256 bytes for the URL to be safe, 2048 bytes for the web page, and then the data traversal, which comes out to an epoch, which is 4 bytes. So one entry into the database comes out to 4308 bytes, which I think is actually padded. Not quite padded. So it would be 2312 bytes if it was padded. Okay, so this is one entry in the database. So then for it would be 20 billion entries. And then 20 billion entries times 2312 comes out to 46.240 billion bytes of data, which comes out to 46.24 terabytes of data, which is also very conservative. A full traversal will probably be more, considering that some like 20 per relevant web pages per website might be a bit on the lower end. There's a lot of stuff on the internet. I think the website number could be higher. So these are our data considerations, and there are also some speed considerations with the crawler. So an average HTTPS request would probably take around 60 milliseconds. So if we're going to be traversing 20 times 1, 20 billion websites, that comes out to 1,200 billion milliseconds, which, if we do the unit conversions, millions, thousands. Comes out to 1.2 billion seconds. Comes out to 13.8 thousand days. So if we turn that to years, that'll take 37 years to crawl the entire internet. So I personally don't have 13 years to crawl the internet, especially considering Google refreshes the internet very often. So a hunch tells me that we should probably multi-thread this crawler. So now we can really start expanding this crawler. So the crawler would have multiple queues to handle this kind of load. And then we could have one shared queue that would hold the frontier. However, if we, let's say, set a limit of 1 million per queue times 56 bytes, comes out to 256 million bytes, 256 megabytes, which is very reasonable for a queue. So if we have a 1 million link frontier, that's very reasonable. We could manage that on one computer. We don't need to multi-thread that. The visited, we could hash these URLs. So if we hash it, we could run into like a SHA-256, which 256, that comes out to 256 bits. That by 8 comes out to 32 bytes. So 32 bytes per address. And then we have 20 billion entries because we don't want to run into a cycle. So 32 times 20, it's 640 billion bits, which comes out to 640 billion bytes. That comes out to 640 gigabytes. So we could probably break this up into different, we could probably break the frontier into different computers. We could probably manage it on one computer, but it's a lot. So we can break it up into multiple computers. And then we would have to have some sort of visitor manager, which we'd have to have some sort of sharding mechanism for managing that. We can use our own internal version of like memcache or something, and this sharding mechanism will manage the visited cache nodes. So we can have multiple of these. So we now know that we probably need a lot of crawlers in order to do this in a reasonable time. If we can an extra crawler would basically have this number. So if we want to crawl it within, let's say, our goal is to crawl the entire internet in one day. And in order to get to one day, that comes out to we would need 116 computers to do that. So let's just run a basic simulation. We would need 116 computers in order to do that. So that's how many crawlers we would need to manage. And that would add it into our resources. So we can get if we want to go into the fine grain of things, it costs about $36 for an EC2 instance per month. So 36 times 116 comes out to $1,176 per month to crawl the entire internet for the computers alone. And then HTTP processor, we can probably divide this into multiple threads. The processing should be quick. The hardest part is retrieving the data from the network. So this will probably take less than 1 second. We really don't need multiple computers for this. Every 60 computers will need 1 extra HTTP processor. So if we run at peak efficiency, we would need probably 2 of these, 2 to 3 at most. So we could, if we were to multi-thread this, then we would want some sort of queuing mechanism in between it. So move everything down. And then this is just a byproduct of the HTTP processor. I don't think we really need to have a queue for that. And then information into the DB. The throughput for SQL or some sort of database probably isn't fast enough to manage this. So let's say if it was like 5 milliseconds latency, that means for every we need 5. We need some sort of queue to hold it for every 5 entries. We would need 1 computer, 1 SQL instance to process that. So we need 5 SQL instances to manage 1 HTTP processor because it's running at 1/5 of the efficiency of the HTTP processor. So we need some sort of data queue so we don't drop entries. I'm going to zoom out so you can see this. And for every entry queue, we could either have the queue be extremely large or have multiple information entry nodes that are all managing it. And then it could all be writing to different disks or different databases or the same database. So we would need to have a very write-heavy database. So this could be a custom solution. Yeah. This would be how I approach the question of designing a web scraper. This is all done live, so this is the live way of doing it. You can see that this is a very write-heavy and network-heavy program. So we would need a lot of crawlers in order to manage this. Queuing is not that huge of an issue. However, information entry and storage is going to be a big issue. You can see that this, for something like Google, is very advanced because you would need a lot of computers, a lot of compute power in order to hit all these websites. There's a lot of information out on the internet, and Google refreshes it around 5 days. So just being able to do that means they already have a lot of compute power, a lot of data centers managing this. So this is the basic premise of writing a web crawler. If you like this, like and subscribe for more of my videos. And if you have any questions, leave them in the comments. If you are interested in a copy of this, I might upload a link to the YouTube video, or you can check my Medium articles. You can follow me for more articles on that. Thanks for watching. Check me out on Instagram, LinkedIn, GitHub, and Medium. And good luck on your interviews. Peace.